Sets are the most basic building block in all of discrete math. Everything else in this course, functions, relations, graphs, is built out of sets underneath. A set is simply an unordered collection of distinct objects. Order doesn't matter, and duplicates don't count. The set containing 1, 2, 2, 3 is exactly the same set as the set containing 1, 2, 3. We write A is an element of B to mean A is a member of the collection B, and A is a subset of B means every single element of A is also an element of B. Formally, for all x, if x is an element of A, then x is an element of B. First key theorem, inclusion-exclusion for two sets. The size of a union B equals the size of A plus the size of B minus the size of A intersect B. Inclusion-exclusion for three sets extends this idea. The size of A union B union C equals the size of A plus the size of B plus the size of C minus the three pairwise overlaps. A intersect B, A intersect C, and B intersect C plus back the triple overlap, A intersect B intersect C. Power set size. The size of the power set of A, meaning the set of all possible subsets of A, equals 2 to the power of the size of A. And De Morgan's laws for sets, the exact same pattern as logic, but now with union and intersection instead of or and. The complement of A union B equals the complement of A intersect the complement of B, and the mirror version. The complement of A intersect B equals the complement of A union the complement of B.
Here's the proof sketch for why the power set has exactly 2 to the n subsets. For each of the n elements in A, you face exactly one binary decision. Is this element in the subset you're building or out? Two choices, completely independent for every element.
Multiply those choices together across all n elements. 2 times 2 times 2, n times over, giving 2 to the power of n total possible subsets. Here's why inclusion-exclusion works. It corrects for double counting. When you naively add the size of A and the size of B, anything sitting in both sets gets counted twice. Subtracting the overlap exactly once cancels out that duplicate, leaving the true total. The trick is simple but works every time. Draw the Venn diagram every single time, even under exam pressure. For three set problems, fill in the innermost region first, the triple overlap in the very center, then work outward region by region. Worked example A. The size of A is 20, the size of B is 15, and the size of A intersect B is 5. Find the size of A union B. Apply the two-set formula directly. 20 plus 15 minus 5 equals 30. So the size of A union B is 30. Worked example B. A genuine three-set problem. A survey of 100 people finds 45 like tea, 40 like coffee, 30 like juice, 15 like both tea and coffee, 10 like both tea and juice, 12 like both coffee and juice, and 5 people like all three. How many people like none of the three? Step 1. Apply the three-set inclusion-exclusion formula. 45 plus 40 plus 30, minus 15, minus 10, minus 12, plus 5. Step 2. Add the singles. 45 plus 40 plus 30 equals 115. Step 3. Subtract the three pairwise overlaps. 115 minus 15 minus 10 minus 12 equals 78. Step 4. Add back the triple overlap. 78 plus 5 equals 83. So 83 people like at least one of the three drinks. Step 5. Subtract from the total surveyed. 100 minus 83 equals 17 people who like none. And this checks out region by region too. Only tea, only coffee, only juice, each pairwise only region, and the triple overlap all come out non-negative, and they sum to exactly 83, confirming this is a genuinely realizable set of numbers. Worked example C. Power sets. List every element of the power set of the set containing A, B, C. Step 1. The size of A is 3, so the size of the power set is 2 cubed equals 8 subsets total. Step 2. List them systematically by size. The empty set, size 0, then the three singletons, just A, just B, just C, then the three pairs A and B, A and C, B and C, and finally the full set itself, A and B and C. Count them up. 1 plus 3 plus 3 plus 1 equals exactly 8, matching the formula. Common mistakes to watch for. First, confusing subset of with proper subset of. Subset of allows A and B to be exactly equal. Proper subset of requires them to actually differ. Second, forgetting that the empty set is a subset of literally every set, including itself. This trips people up constantly when counting subsets. And third, in 3-set inclusion-exclusion, forgetting to add the triple overlap back in after subtracting all 3 pairwise overlaps. That's the single most common arithmetic slip on this topic.